to the course. Last weeks I have talked about some parameters in related earthquake and earthquake hazard, and I have talked about magnitude, amplitude, and some parameters about some hazards and earthquake location and occurring earthquake and seismogram. Today I am going to have a very short overview about seismology and maybe both earth layers as chemical layers and mechanical layers division, and properties of each layers of earth. Also, I am talking about earthquake occurring and tectonic plates. Also, why earthquake occurring. As mentioned before, I had a description about seismology and the branches of seismology and some explanations about seismology. Seismology, in fact, is a science dealing with all aspects of earthquake as observational seismology, engineering seismology, or physical seismology. Observational seismology is the branch of seismology that includes recording earthquake as macro seismology, also cataloging earthquakes and observing earthquake effects as macro seismology. Another branch of seismology is engineering seismology. The engineering seismology has estimations of seismic hazard and risk, also about seismic buildings. And another branch of seismology is physical seismology. The physical seismology include a study of the properties of the earth interior and a study about physical characteristics of seismic sources. Seismology, in fact, is a science as a multidisciplinary science links physics with other geoscience as such as geology, geography, international science, and about large span of amplitude, uh, about 10 to the power minus 9 to 10 to the power 1 meter as a displacement and amplitude. Also, very large span of wave period around 10 to the power minus 3 to 10 to the power 4 second as a wave periods. Very young science, second half of the 19th century. That's we have some study about the seismology. As myths and legends about earthquake occurs, we have some definitions about and describe about earthquake occurs in some culture as different definitions and descriptions. And as a Hindu culture, Mongolia culture, Africa culture, Japan, that's describe about the occurring the earthquakes. In the Hindu, some people believe when one of the 8 elephants that carry the earth gets tired, the earthquake occurred. In Mongolia, some people believe when a fork that carries the word moves, the earthquake occurring. And another in Africa, some people in Africa believe in the giant one house head where we all live, sneezes or scratches, the maybe the earthquakes occurred. We have another description about occurring the earthquake in Japan. Some people believe that when the attenuations of the god Kashima, who looks after the gaunt hot fish and Namazo that supports the earth and prevent in the sink into the ocean weakness and Namazu move and the earthquake maybe occurs. In this slide, some the schematic pictures about the regions of earthquake occurs shows and some descriptions of some cultures uh, shows and describe for you. Another one, some people believe in the god my must decide to count the population, improve his footsteps, shakes the earth, then native run out of their holes and yell, I am here, and so we have earthquake. This is some descriptions and believing about the earthquake in some cultures in some countries. Next slide shows the slice of into earth. You can see we are going to show you how the earthquakes really occur. We first need to learn about constitutions of the earth. In this slide, you can see the earth as chemical radial divisions divided three major layers that call crust, mantle, and core. Also, as mechanical divisions, the earth inside earth divided three layers as asthenosphere, lithosphere, and mesosphere. Also, this slide shows the properties of each layer uh, as pressure and temperature. Also, the properties of each layer as chemical properties. As a divisions of the chemical layer of Earth, the shallowest layer of the Earth named is the crust. The crust is the most heterogeneous layer in the Earth. The crust is is average around 32 kilometer thick for continuities and 10 kilometer thick bench oceans. However, it varies from just a few kilometers to over 70 kilometers globally. Also, the crust include continental and ocean crust. The boundary between crust and mantle called Mohevich is continuity and maybe Moho called. Also in this shape, as you can see, the temperature and pressure increase with depth. Middle layer of Earth called the mantle. Earth's mantle exists from the bottom of the crust to a depth of 2,891 kilometer, radius of 3,080 kilometers. Mantle separated with core by Gutenberg discontinuity. It is further subdivided into the uppermost mantle crust to For 100-kilometer depth, the transitions zone for 100 to 100-kilometer depth, the mid mantle around 700 to 2650 650 kilometers depth. The lowermost mantle layer around 2,650 to 2,891 kilometer depth. That is in the depth. The uppermost mantle is composed dominantly of olivine laser component include pyroxene, nestati, and garnet. Third layer of earth as chemical compositions called core. Owing to the great pressure inside the Earth's core is actually freezing, and the Earth gradually cools. The boundary between the liquid outer core and the solid inner core occurs at a radius of about 1,250 kilometers, and that's separated uh, with mantle, the core with mantle by the Gutenberg discontinuity, and outer and core, inner core and outer core divided and separated with Lemon discontinuity. After Inge Lemon from Denmark, this is scientists that's called the Lemon discontinuity. The boundary between the mantle and outer core is sharp. The viscosity of the outer core is similar to that of water. It flows kilometers per year and creates the Earth's magnetic fields. The outer core is the most homogeneous part of the Earth, and the Earth the outer core is the most homogeneous part of the Earth, and the outer core is mostly an alloy of iron and nickel in liquid form. As the core freezing intent, heat is realized. This heat causes the outer core to convect and so generates a magnetic field, as you can see in this schematic shape. In this slide, you can see some properties of shallowest layer, crust, and the next slide shows the crustal thickness in everywhere of the world, as shown in ocean and continental thickness. Next slide shows the mantle properties and the depth of mantle everywhere of the world and Earth. This slide shows some properties of the Earth cores, as include two classifications: outer core and inner core. The boundary between the liquid outer core and the solid inner the core at a radius of about 1,220 kilometers. That is discontinuity and names Lyman. The properties of outer core look like solids and include more iron and nickels. In the solid form, and also in inner core we have iron and nickel, but in the liquid form. Next, next in this slide, as shown in schematic shapes, and that's divided the earth in three mechanical layers: lithosphere, asthenosphere, and mesosphere. Maybe in last slide you can see better the three mechanical layer of Earth. As a properties of lithosphere, the lithosphere is the uppermost 50 to 100 kilometer of the Earth. There is not a strict boundary between the lithosphere and the asthenosphere as there is between the crust and mantle. The consists of bed crust and upper part of mantle. It behave rigidly like a solid over very long time periods, as you can see in the schematic shapes. In this slide, you can see the schematic shapes of the lithosphere sections inside Earth. Some part of the lithosphere, in fact, inside the mantle, and some part liquid and in core liquid outer part, and some part of lithosphere, in fact, inside inner core as solid form. You can see in this schematic shape section. The asthenosphere exists between depth of 100 to 200 kilometers, and it is a solid over short time scales, but we have like a fluid over millions of years, and the asthenosphere decouples the lithosphere as a tectonic place from the rest of the mantle. In fact, about the tectonic force can talk the interior of the earth is dynamic, it cools down and thus provides the energy from convective currents in the outer core and give maybe some vibrations as emotions of the tectonic plates. Additional energy comes from radioactive debris inside the core, come in the fault and then give some moving in the tectonic plates. It's shaking or moving one around another and maybe give the shaking and then transfer with the waves inside the holes and coming underground and give realize the energy on the ground, maybe uh, give some answer in related the realized energy come inside the tectonic plates on the ground. In this slide shows the convection in the asthenosphere enables tectonic process and plate tectonics. Plate tectonic theory is very young, around 1960. Until now, it provides answer the most fundamental questions in seismology, such as why earthquake occur, why are earthquake epicenters not uniformly distributed around the globe, at what depths are there foci. We describe about these questions as follow. In these maps, show 1 year of seismicity and shows the numbers of the earthquake occurs in 1 year around 2002 to 2003 in every place. Show the number use of the that earthquakes occurred. As you can see, these earthquakes occurs between tectonic plates. In this map shows the major tectonic plates and then followed under the mesosphere layer. We have the North American plate, or Euro-Asian plate, African plates, South America plates, and Australian plates, Antarctic plates, as show the major plates in the world, and show the plates boundary in these maps. For more study and investigation, you can use some reference and sources that uh, I have seen before. Sorry. Tectonic plates are a large part of lithosphere floating on the asthenosphere, and convective current move them around the velocities of several centimeters per year. The plates interact with one another in three basic ways. Some plates they collide and give collisions and shaking. Some tectonic plates they move away from each other. In third cases, some tectonic plates they slide one past another and give shaking and release energy shaking. The plates interact with one another in three basic ways. First way they collide. Second way with they move away from each other. Third way they slide one past another and then give earthquake on the ground with the interact one another in these waves. Collision is subjected of one plate under another. Mountain range may also be formed, Himalaya, Alps, etc. It produces a strong and sometimes a very deep earthquake up to 700 kilometers. Also, volcanoes also occur there in this area. For example, in this slide shows Nazuka, South America, and Eurasia Pacific tectonic plates, and then show schematic shapes about collision, list of subjections of one plate under another, and give instructions on the ground. Next slide show interacting plates. Plates moving away from each other and produce ridges between them, spreading centers as shown in the schematic. For example, Mid-Atlantic ridges, African, South American plates, and Eurasian, North American plates. The earthquakes are generally weaker than in the case of subduction. In schematic shape, as you can see, the between ocean and plates, the spreading centers, the convection, and also shows the plate tectonic process as the moving away from each other produce rigid between them and a spreading center. Next slide shows the interacting plates ways in schematic shapes as the fault zones between plates and moving the part of blocks in near faults. Plates moving past each other do so along the transform faults. The earthquake may be very strong. For example, that shows the San Andreas Fault, Pacific North American plates. In case A, show the schematic shapes of divergent, merging. Case B, show the convergent, margin, subductions in the fault, and ocean trench, continental crust, and as in the lithosphere layers, and show the interacting plates in the lithosphere layer floating under asthenosphere layer. That occurring inside the fault between ocean trench and the continental crust. In case C, show on convergent margin oscillation. Case D, show transfer inside fault merging as transfer fault flux. Next slide show how earthquake occurred after descriptions about the moving the tectonic plates waves. We are going to describe the how earthquakes occur. Earthquakes, in fact, occur at faults. What is the fault? Fault is weak zone separating two geological plates. Tectonic forces maybe case about the radioactive forces, case the blocks to move relative one to another, as shown in these schematic shapes that show the fault as a moving as normal fault, reverse fault, and strict slip fault. In three cases, shows the fault block can move and give destruction. As normal fault, reverse fault block moving also can the block faults moving in fact or transfer as a strike slip fault. Next slide shows the elastic rebound theory related the faultings and earthquakes, and show the a picture from come from fence office in 1906 quick earthquakes on San Andreas faults and some schematic shape of the moving the fault blocks. Next slide shows the schematic shapes of the faults as the moving the blocks fault in some ways. In first schematic shapes shows in upside, and the right side shows the fault in original positions, and as show the position fence and original positions of the fault blocks. After earthquake occurring, the original position change and give the formation looking like the formation in right side, left side chain to right side schematic shapes. Maybe rupture and release of energy, maybe rocks rebound to original undeformed shapes, as you can see in the schematic shape. This is because of friction. The blocks do not slide but are deformed when the stress within the rock exceeds friction. Rupture occurs, and then the fault give failure. Also, elastic energy stored in the system is released after rupture in waves that radiate outward from the fault. The elastic wave or body waves include longitudinal waves and transversal waves. As a properties of longitudinal waves can describe include they are faster than transfer wave and thus arrive first. The particle oscillate in the direction of spreading of the wave. Also, that's called compressional wave or primary wave and P waves. Also, some called P waves. As a properties of transfer waves, the particle oscillate in the direction perpendicular to the spreading direction. Shear wave, they do not propagate through flows through the outer core than transfer just in the solid material. The transfer waves also transfer uh, waves also called S wave or shear wave. Next slide shows the schematic shapes of P waves and S wave directions as a schematic shapes. In the P wave, the direction, the particle emotions look like the uh, emotion of the wave. Uh, in fact, as a deformation propagation, particle motion consists of alternating compression and dilation. Particle motion is parallel to the direction of propagation uh, of the wave emotion. And material returns to its as S wave direction, deformation, propagation. Particles motion consists of alternating transfer motions. Particle motion is perpendicular to the direction of propagation or transfer. Transfer particle motion shown uh, are, the vertical but can be in any direction as a case mostly vertical SV or maybe SH. I will to I will try to change the slide as the animations in the PowerPoint. Okay, this shows the wave animations from the transfer or S wave or shear wave that show the directions of the particles and directions of the wave emotions. As you can see, the particle motion consists of alternating transfer motion. Particle motion is perpendicular to the direction of propagation. Transfer particle motion shown here is vertical but can be in any direction, S wave or maybe SH, as horizontal and vertical on the surface. This slide show P wave emotion. As a body wave, we have two type body waves, include the P wave and S wave, and another type of wave called the surface wave, as a love wave and ray wave. Elastic wave in another type called surface wave include rail wave and love wave, as shown in these schematic shapes. In a rail wave, As a deformation propagates, a particle motion consists of elliptical motion, generally retrograde elliptical in the vertical plane and parallel to the direction propagation. Amplitude decrease with depth. Material returns to its original shape after wave passes. Surface wave include rail wave and low wave. Their amplitude dimension with the depth. They have large amplitudes and are slower than body waves, include P wave and S wave. There are dispersive wave, large period are faster. This as a differences between surface wave and uh, body waves. In the love wave or L wave, deformation as a deformation propagates, particle motion consists of alternating transverse motions. Particle motion is horizontal and perpendicular to the direction of propagations or transverse. To aid in seeing that the particle motion is purely horizontal, focus on the y-axis uh, as the wave propagated through it. Amplitude decreases with the depth. Material returns to its original shape after wave passes. You can see the in next slide the schematic shape of the S wave emotion as a particle direction and wave direction in the propagation. Also here show the schematic animations of direction of propagation rail wave in the particle direction and railway direction emotion. As shown in this animation, particle motion consists of elliptical motion, generally retrograde elliptical in the vertical planes and parallel to the direction of propagation. As properties of railway, amplitude decrease with depth, material return to its original shape after wave passes. In this animation shows the compressional wave or P wave or primary wave emotion, and also show the direction of propagation of particles, the same size of direction of propagations of wave in same wave motion. Particle motion consists of alternating compression and dilation. Particle motion is parallel to the direction of propagation in this slide. These animations. This animation shows the shear wave, S-wave animations, and then is so clear to show you the propagation of and distributions of the S-wave. Particle motion consists of alternating transfer motion, and particle motion is perpendicular to the direction of propagation. And the direction of particle in transfer of motion, the wave propagation. Here show that transfer particle motion show vertical but can be in any direction. However, outlier tend to case mostly vertical SB is shear vertical in the vertical plane, or horizontal SH in horizontal plane as shear motions, and material returns to its original shape after wave passes. Next slide show railway animation and show the direction of propagation, wave propagation, and particle motion direction as animation schematic. Particle motion consists of elliptical motions, generally regard elliptical in the vertical plane and parallel to the direction of propagation. Amplitude decreases with depth. Material returns to its original shape after wave passes. Next slide shows love wave animation. In this love wave animation shows direction of propagations during the love wave and the motion of particle direction. Particle motion consists of alternating transfer motions. Particle motion is horizontal and perpendicular to the direction of propagation. To aid in seeing that the particle motion is purely horizontal, focus on the y-axis, show with red line. As the wave propagates through its amplitude decreases with depth, material returns to its original shape after wave passes. Next slide shows the seismogram that's record the earthquake in Japan. It station in Germany by amplitude magnitude 6.5 and shows the recording the P and S wave as a surface wave per times recording. Another also shows the another seismograph, and seismographs are devices that record ground motion during earthquake. The first seismogram were constructed at the very end of the 9th century in Italy and Germany, as shows in this picture. Strasbourg, 1982. And in this slide shows one seismograms and in schematic shapes, and also a picture of a seismograph in Zagreb built in 1909. Horizontal 1000 kilogram Richard seismograph in Zagreb built in 1909. Show in this picture the instrument of this seismograph. Left side show the schematic shape of seismograph instrument that's come from 1999. John, Willie, and Spence. As mentioned before, the seismograph are devices that record ground motion during earthquake. In the magnitude form, maybe the velocity of wave, accelerate of wave as the velocity of wave per time, or accelerated wave per time, or the amplitude of wave per time can record. In the sum curve. Next slide show another seismographs instruments. That is modern digital broadband seismograph are capable of recording almost the whole seismograph spectrum, 50 hertz to 300 seconds. There's the resolutions of 20 bits high dynamic range allows for precise recording of a small, quick, as well as unsaturated registrations of the largest one, and show the data logger to record results. Next slide show the maps of urban seismological station in Europe and occurring earthquake numbers. We are now equipped to start recording. For that, we need a seismic network of as many stations. Minimal number of stations needed to locate the positions of an earthquake epicenter is three. We need three stations to record the earthquake to find the earthquake epicenter at minimum, as mentioned before. Next slide show the observational seismology and show a picture from 1969 to 72 from Apollo astronaut placed a seismometer on the moon, and the first moon quake are registered. Next slide show describable locating earthquake. To locate an earthquake, we need precise readings of the times when P and S wave arrive at a number of seismic stations. Accurate absolute timing with a precision of 0.01 second is essential in seismology, as shown in one recording of first P wave and first S wave per times in this slide as a curve recording graph. Now we knowing the difference in arrival times of two wave and knowing their velocity, we may calculate the distance of epicenter. This is done using the travel time curves, which show how long does it take for P and S wave to reach some epicenter distance. We have the distance, and also we have the velocity. We have time, so we can calculate the distance. As shown in this curve, we have the differential between times and the distance differential. Then we can calculate velocity. Velocity equal the differences between distance per differences between times arrival, as shown in this picture equation. In this slide, show another example of picking arrival times that show the graph of recording the arrival times of the wave per times. As mentioned before, we need three stations at minimum recording to find the epicenter of earthquake occurring. After we know the distance of epicenter from at least 3 stations, we may find the epicenter like this show in this picture map. We have 3 stations recording. We can find in the of this 3 station recording the location of epicenter of earthquake occurring. There are more sophisticated method of locating positions of earthquake forces. This is a classic example of an inverse problem. In this, we have some reference and sources for study more and highly recommended to reading and study. You can use some sources in internet and some paper to more understanding. As shown in this slide, some sources.
Now.
If let me, I want to change my PowerPoint, and we are going to continue with next PowerPoint. Okay. Uh, next step, we have descriptions about magnitude of earthquake. About we want to explain more about determining the magnitude of an earthquake. In fact, the magnitude is a measure of energy released during earthquake. There are several different ways to measure magnitude. Most common magnitude As mentioned before, major is uh, with Richard magnitude named for the renowned seismologist Carlos Richter. In Richter magnitude, measure amplitude of largest S wave on seismograph record and also take into account distance between seismograph and epicenter. Also, we have Richard scale as a properties of a Richard scale for magnitude. Uh, the Richter scale are based of logarithmic numerical scale, not a physical. Also has properties of Richard scale magnitude, include increasing one whole unit on Richter scale represent 10 times greater magnitude. Going up on whole unit on Richter scale represent about 30 times greater release of energy. Another parameters is intensity. Intensity refers to the amount of damage done in an earthquake. And we have Mercalli scale for intensity is used to express damage. The seismic moment is a physical quantity as opposite to earthquake magnitude that measure the strength of an earthquake. It is equal to uh, G times A times D. G is the shear modulus, A equal L times W is the rupture area, D is the average co-seismic slip, as shown in this slide shape. Show the D rupture, average co-seismic slip, and also show L and W, L in vertical direction and W in horizontal direction based on the fault plan. It may be calculated from the amplitude spectra of the seismic wave. Seismic intensity scale often referred to as the Mercalli scale quantifies the effects of an earthquake on the Earth's surface, human objects of nature, and man-made structure on a scale of the draw 1, draw 2 from this definition from Wikipedia. For example, as show the intensity scale 1, 5, 8, or 12. In intensity 1 scale, shaking is felt by a few people. In scale 5 as Mercalli intensity scale, shaking is felt by almost everyone. In the scale 8 case great damage to poorly built structure. In 12 scale of Mercalli intensity, we have total destruction. That means everything, destruction and collapse and failure. In this figure shows the collapse of building as a function of intensity of shaking. In the vertical axis show percentage of building collapse between 0 to 100%. In horizontal axis show modify Mercalli intensity scale and show the area of the every collapse and magnitude of collapse of buildings as a function intensity. In level 5 to 6, we have not any more distractions, just we have 0.2 G damage onset for modern buildings. In level below 5, no destruction. Level 6 start destruction and collapse, and then increase in level 11 and 12 until destruction all things. First destruction, fire brick. Second, next with increased scale of intensity, time wireframe, then destruction, reinforced concrete. In last level of intensity, the reinforced concrete and RC anti-seismic, everything collapse, total collapse, and the failure and destruction. Okay, I think for today is enough. If you have any questions, I am here to hear and answer. Please let me know if you have any questions. I think everything is clear, and somehow we talking some things that all right in the PowerPoint, and you can also after these presentations you can also study more and read on the PowerPoint if you somebody less understanding any problems. If you have any questions, please ask. Any questions? Okay, no question. Thank you very much for your consideration. For today is enough. we continue next week on the time. Have a good bye. Thank you very much. Bye.